Okay, today we're going to take a look at implicit differentiation. Implicit differentiation allows us to take the derivative even if we don't have a function in the form of y equals a function of x. Okay, here we have x squared plus y squared equals 1. This is a circle with radius 1. And we might want to find the slope at any point along this circle, even though this is not a function. So we take the derivative of both sides with respect to x. So we're going to take the derivative of x squared with respect to x. There's nothing new there. We're going to take the derivative of 1 with respect to x. Nothing new there. Where we run into something a little bit different is we take the derivative of y squared with respect to x. And notice those variables do not match up. So the derivative of x squared is 2x. The derivative of 1 is 0. But the derivative of y squared is 2 times y times dy dx, because we use the chain rule here. Our outer function is that exponent of 2. Bring that down, keep the inside the same. If we take the derivative of y with respect to x, that's what we call dy dx. So now we're going to rearrange because we're trying to get dy dx by itself. So subtract 2x and divide by 2y. We can cancel out those 2's, and now we can find the slope at any point along this curve is equal to negative x over y. All right, here's another equation that is not a function, but we might still want to talk about the slope at any point along that curve, or the derivative dy dx. So we take the derivative with respect to x. The derivative of 2y with respect to x is 2 times dy dx. The derivative of x squared with respect to x is 2x. And the derivative of sine of y with respect to x, so we use chain rule here. The derivative of sine is cosine, leave the inside the same, so cosine of y, times the derivative of the inside. The derivative of y is dy dx. Now, whenever we take a derivative this way, we want to get dy dx by itself. So our strategy for doing that is to get the terms that contain dy dx on one side of the equal sign. So in this case, we subtract cosine y dy dx. We can factor out the dy dx, and then we can divide. And now we have dy dx by itself, and we see it's equal to 2x over 2 minus cosine of y. And so the interesting thing here that we haven't seen up until this lesson is our derivative is dependent not just on x, but also on y. So this is what we refer to as implicit differentiation. And the way we go about this, take the derivative of both sides with respect to x, and then always get dy dx by itself. Okay, so we want to find the equations of the tangent and normal lines to this curve at this point. So if we're going to find a tangent line, we need to have a slope, which comes from dy dx. Okay, so derivative of x squared is 2x. Now be really careful right here. The derivative of x times y, that's a product of two functions, so we have to use product rule. Take the derivative of x, you get 1 times y, and then we can leave the x alone, and the derivative of y is dy dx. The derivative of y squared is 2y dy dx, and the derivative of 7 is 0. So we distribute that negative through the brackets there, and we're going to get dy dx by itself on one side of the equation. Everything that doesn't contain dy dx moves over to the other side of the equation. Divide by 2y minus x, and we get dy dx all by itself. So the slope at this point, negative 1, 2, we plug in both of those for x and y, and we find that the slope is 4/5. So the tangent, y minus our y value equals 4/5 times x minus our x value. And the normal, all we have to change there is use the negative reciprocal for the slope to find the perpendicular line. Okay, and we can find higher order derivatives using implicit differentiation, meaning we can find the second derivative or possibly the third or fourth. Typically, we won't go beyond the second derivative. So we want to find the second derivative of this equation. So first, take the derivative of both sides. Notice I'm using a different notation here. Instead of dy dx, I'm just using y prime. They're interchangeable. You could use one or the other. Knowing that I'm going to be taking the second derivative, I know that using this notation right here is going to make my work look a little bit cleaner. So get y prime by itself, simplify, This is one case where you definitely do want to simplify no matter what, because it's going to make the work for the next step much easier. So if you're trying to find the second derivative using implicit differentiation, you really should simplify as much as you can after taking that first derivative. So now y double prime, that's the derivative with respect to x of x squared over y. So we have to use quotient rule, low d high minus high d low over the square of what's below. And notice the derivative of y, we just write y prime. And we could simplify this, not absolutely necessary, but I'm going to go about it this way here for this example. And when I find the second derivative, I want it to be entirely in terms of x and y. And the way we can get that is by now replacing y prime with our function for y prime, or not our function, but our equation for y prime that we found previously, x squared over y. So we plug that in and simplify it down, and there's our equation for the second derivative. Let's take a look at what our calculator can do. We can tell it to find the second derivative. We use this right here in your catalog, implicit differentiation. And always look at the bottom to see what your notation should look like. We want to type in our equation, the variable, so that would be the independent variable, the dependent variable. And whenever you see this notation where there's a bracket, that's an optional command. And ORD stands for order, meaning is it the first derivative, the second derivative, and so on. So in this case, if we want to find the second derivative, we're going to have to put in a 2 right there. So implicit differentiation, our equation, x, y, and 2, because we want to find the second derivative. And there we go.